Can an electron be both blue circle and a red square? Kinda. Einstein couldn't accept the logic behind this weird identity crisis, but in quantum world, it's just another Tuesday. To see why he was so bothered, let's use an analogy, just so that our brains don't melt. Imagine an electron has properties like color, shape and pattern. Now say you measure this little guy's color and shape. You find that it's a blue circle. But then you measure it again. Only this time you check the color and the pattern instead. Suddenly the electron is red and striped. What happened? Did the electron suddenly change its mind about what color it is? This question was the center of decades-long battle between the greatest minds in history. On one side was Einstein. He was a realist. That's what science bros call when someone likes things certain and definite. To Einstein, if an electron looked blue in one test but red in another, it wasn't changing, we were just missing something. He was convinced that every particle carried a hidden list of answers for every possible measurement, even the ones we haven't made yet. As he once said, "I like to think that the moon is there even when I am not looking at it." But as it turns out, quantum particles don't play by standard rules. Before you measure that electron, it's in a state called superposition. You have probably heard of this through the famous Schrödinger's cat. The idea that a cat can be both dead and alive until you actually open the lid to check. In our case, the electron isn't just one thing. It's a blur of all possibilities. Literally blue and red, circle and square. But here's the catch. In quantum world, you cannot just observe an electron from a distance, so you actually never see this blur of possibilities. To know anything about the electron, you have to get your hands dirty. You have to hit the electron with a photon or trap it in a magnet. You just have to interact with it, one way or another. And the moment you do, that blur of possibilities is forced to settle in a single boring fact. Which brings us back to the Einstein's big problem. Was that result rigged from the start? Was there a hidden master list or a secret algorithm that already knew answer to your test and every other test you could possibly run? This is exactly what Einstein believed. He was convinced that the universe wasn't random, it was just keeping secrets. But in 1967, more than 10 years after Einstein has already died, two mathematicians named Kochen and Specker proved that this hidden master list is logically impossible. They showed that if you try to write down a definite yes or no answer for every possible question you can ask a quantum particle, you will run into logical contradictions. Then it took nearly 50 years to move from these theoretical predictions to actual reality. Recently, in 2022, scientists finally proved this with an experiment. I'm going to simplify this experiment by about 99% for the sake of you and me. Imagine an electron. It doesn't have properties like color and shape, but it has another properties, such as spin and energy. If you don't know what the spin is, just think of it like a tiny magnet that can point in any direction. The scientists prepared an atom where the electron could hang out in two energy levels, state 1 or state 2. Then they started asking the electron some questions by simply measuring it. The first question was, are you in state 1 and is your spin pointing right? The electron answered yes and yes. But then they asked a second question. Are you again in state 1, but this time is also your spin pointing up? And suddenly the electron says no and no. Wait, what? It just told us it was in state 1. Why is it suddenly changing its mind about its energy level? Just because we asked about a different spin direction? Well, the reason is that the energy of this electron isn't fixed. The value we measure doesn't just depend on what we are measuring, but also how we are measuring it. For example, what else we are measuring at the same time. This means we cannot think of a measurement as simply revealing a property that was already there. And this is exactly what we call quantum contextuality. Basically, the reality we see isn't a secret the particle was hiding. Instead, it's a specific response to the way we decided to interact with it. So we have to stop thinking of properties as simple labels that are stuck onto the particles. They aren't things particles are. They are responses to how we interact with it. This is the heart of the mystery. We used to think that the universe was world of labels, where things have fixed properties even when nobody is interacting with them. But the math of the quantum world shows that we live in a world of relationships. In this world, properties like electron spin or energy aren't fixed. They only exist in relation to other properties. So the next time you feel like you don't have your life together, just remember, neither does the universe until someone forces it to make a decision.